Okay, so I think this is what we are going to look at today. We say including unit vectors. Okay, so if we talk of three-dimensional vector and two-dimensional vector, they are quite different, but they are the same. They are the same in a certain way around. Why? Because they all involve the issue of finding the magnitude and the angle. Now, as for three-dimensional vector, questions comes in a different way around. Then you will find that under three-dimensional vectors, if we say three-dimensional vectors, it is different from two-dimensional vector in such a way that under two-dimensional vector, you'll find that a vector can be given like this. We are going to have the resultant here. Okay, if you have a resultant somewhere there, then here they can give you x component, which is going to be equal to, then you say r cos theta, right? Then this one, which is my y component, we said it has to be equal to r sine theta. Okay, so this is according to two-dimensional vector. How do you find the angle? How do you find the resultant, or rather the magnitude for two-dimensional vectors? We said we find the magnitude for two-dimensional vectors by saying r has to be equal to root of, by the way, this has to be r x, the resultant in x, and this one has to be the resultant in y. So we say r x square plus r y square. That's how we find the resultant of what? Of two-dimensional vectors. And then for the so-called direction, direction simply means the angle that is made by the resultant. So we normally use the identity for what? Tangent. We say tan theta has to be equal to, we look at in a scenario whereby we know that the y component is movable. It can move. It can even come to this given end. But the x component can't even move, and then our thing is going to be like this. This has to be my resultant. This one has to be my x component, and the y component can be given at this part. So since this is my y component, and you want to find the angle here, using SOHCAHTOA, I think we still remember if you use SOHCAHTOA. And last time, if we had to get back a bit to that same lesson that we had, we said these two identities, they are used to find the what? The components. The remaining identity, which is tan, and tan is given as what? We say tan theta has to be equal to, the opposite here has to be the y component. And then the adjacent, which is a, has to be the x component. That's why for you to find the direction, you have to say tan theta has to be equal to ry over rx. So the answer you're going to get here for ry after resolving this given resultant into its components, or after getting the total of all the resultants, we said that's what you are going to put where there is ry. Same applies to rx. That is according to two-dimensional vector. That is according to two-dimensional vector. To find the resultant, or rather the magnitude of the resultant, we normally use this formula whereby you've been given the resultant in x and the resultant in where? In y. To find the direction, we use this given formula. Now, how is two-dimensional vector different from three-dimensional vector? For three-dimensional vector, from the word itself, three-dimensional, it simply means we introduce a certain component. That is what we call a z component. So if we have something like this, z component can be introduced by facing in this given direction, meaning that this is going to remain as y component, this one is going to be my x component, and this one is going to be my z component. So the resultant, my resultant can lie in this given path r. So since this is my resultant, the resultant must have all the three components. It will have y component, x component, including the z component. Now, how do you find the magnitude of three-dimensional vectors? How do you find the resultant or rather the magnitude of three-dimensional vectors? It is very, very simple. We find the resultant or rather the magnitude of three-dimensional vectors by just including the z-axis to where? To this formula which we are from having here. Meaning that for three-dimensional vectors, our resultant is going to be what? You say r has to be equal to root of, I'll just say rx square plus ry square plus rz square. Okay, that's how we find what we call the resultant of a three-dimensional vector. That's how we find a resultant of three-dimensional vector. Now, we are going to find that it is totally different. If we are trying to find the angle for two-dimensional vector, we use the components ry and rx. But here, we do not use any component with reference to this one. I mean with reference to any angle if we want to find what the angle the resultant can make. Here under three-dimensional vectors, every component is having its own angle with reference to the resultant. We are going to have the angle from this component here. We are going to have another angle with reference to x component somewhere there. We are also going to have another angle with reference to where? To z component from the resultant. And what are the names given to these same angles? What are the names given to these same angles? So the angle which is made between y-axis, or rather y component, and the resultant, we call it as a beta. The angle which is made between the resultant and the y component, we call it as what? Beta. It has to be something like this. Beta. The angle which is made between the resultant and the x component, we call it as what? Alpha. Something like this. The angle which is made between the resultant and z component, we call it as what? Gamma. Like that. So we find the angles with reference to what? With reference to every component from the resultant. We find the angles here by not using tan, but we are going to use another identity, which is what? Which is cos. If they ask you a question to say, why is it that we do not use tan here to find the angles, and yet we are using what we call cos? The reason is very simple. Here, every component is meant to be my adjacent. Every component here is meant to be my adjacent. And the only identity which relates adjacent and the resultant always has to be your hypotenuse. So you find that if you say cos theta, we are saying it has to be equal to adjacent over hypotenuse. So every angle here has to be with reference to every axis. From x to the resultant, we are going to find its own angle. From y-axis to the resultant, we also have its own angle. From z component to the resultant, we are also going to find its own angle. And how do you find? Remember I said the hypotenuse has to be my what? My resultant, the magnitude of the resultant. Meaning that A here has to be adjacent. What is this A? It has to be every component that you are going to have in that same vector. Hence, the angles for three-dimensional vectors are found as follows. Okay. So the angles for three-dimensional vectors, we find them like this. You just say cos. If you start from alpha, you are going to say alpha has to be equal to what component is making, or what component are we going to use for us to find the angle which is going to be here? It must be x component. This is going to be put on top, I'll say x over the magnitude of the resultant. In short, we find the angles with reference to every axis and the magnitude of the resultant. Firstly, you need to find the magnitude of what? The resultant. To find the angles now, you just pick the x component of that same given three-dimensional vector, you put it on top. You divide by what? By this. To take this one to your right-hand side, it will be like this. We are going to have alpha, it is going to be equal to what? Cos inverse of x component over the resultant. You do like this. So this is going to apply to all the three what? Components. I'll also have cos beta here, which is going to be equal to, this one has to be for y over the resultant. I'll also say cos gamma, it has to be equal to z over the resultant. This is how we find the angles for three-dimensional vectors. We don't find the angle in reference to the resultant whereby you can use tan. Tan only applies to two-dimensional vectors. Tangent only applies to two-dimensional vectors. Alright, okay. So that's how we find the resultant for three-dimensional, and that's how we find the what? The angle for three-dimensional vectors. That's how we find the angle for three-dimensional vectors. An example, let's try to solve an example so that we example. So say find the angles in reference to each axis in the following vector. So I'll say A has to be equal to, I'll say 2x plus y minus 5z minus 5z. So here we normally get the coefficients of every axis. So the coefficient of x here has to be 2. The coefficient of y here has to be 1. The coefficient of z has to be negative 5. And how do you punch, or rather how do you calculate for the angles based on this one, which is going to have a negative? Don't even worry. For sine and cos, we can just punch together with the negative and we are going to get the exact answer without any problem. For sine and cos, we can punch the direct answer and definitely we are going to have the solution without any problem. Okay, we try to solve this. So here, the first thing, before you even start calculating, look at what they're saying with reference to each axis, meaning that you are going to find the angle with reference to x, y, and z. But if they specify to say just find the angle with reference to y-axis, just go direct to y-axis, you find the angle for what? For y-axis. Okay, so now, how do you find the angle here? You have to do this first of all. You find the resultant. So I'll say, okay, so since we are using letter A here, let's try to use A also because they have given us the vector A. So I'll say A x square plus A y square plus A z square, meaning that A has to be equal to a root of, here I'll get my 2 square plus I'll get my 1 square plus I'll get my negative 5 square, meaning that A has to be equal to, we are going to have 4 plus 1 plus 25, and A is going to be equal to root of 13. It has to be square root of 13. So to get the angles, we said we are going to be using cos. For three-dimensional vectors, we must use cos with reference to what? To every component. With reference to every component. So the way this one can be drawn, if you want to illustrate what is happening here, we are going to have something like this. So here we are going to have negative 5x. Here we are going to have y, and somewhere there we are going to have 2x. And yet our resultant is found somewhere in the middle here, A. Okay. So we are going to find the angle here, which is going to be beta. We are going to find the angle somewhere there, which is going to be alpha, and the angle here, which is going to be gamma. Right. So to find the angles, what are we supposed to do? I'll start with the x component. I'll say cos alpha has to be equal to x over vector A. Okay. So here on x we have 2 over, what is the resultant? We are having root of 13. So definitely this is going to be cos alpha has to be equal to 2 root of 30, meaning that alpha is going to be equal to cos inverse of 2 root of 13. We close, meaning that our angle alpha is going to be equal to, when punching on the calculator, you can just punch this directly. We are going to say cos inverse, open bracket, 2 divided by square root of 30. I'll say close. Definitely we are getting the answer as 68.58. Whenever we try to round off this, we are going to have 68.6. Okay, so we are having 68.6 degrees. That is the angle which is made between the x-axis and the resultant, which is A. The angle which is made between the x-axis and the resultant, which is A. Okay. Now we try to look at the angle that is going to be made between the y-axis and the resultant A. So I'll do as wise by saying cos beta, it has to be equal to y over the resultant, which is A. So cos beta is going to be equal to, what is my y-axis? We are saying it has to be 1. So divide this by root of 13. So meaning that the angle beta is going to be equal to cos inverse of 1 over root of 13. So beta is going to be equal to, okay, so I'll just say shift cos inverse of 1, divide this by square root, let's use this calculator. Say shift cos inverse of 1 divided by root of 30. I'll close. We are getting 79.48, which is going to be equal to 79.5 degrees. 79.5 degrees. Okay, that is the angle which is made between the resultant A and the y-axis. If we go to z-axis, which is having negative 5z, we are going to say cos gamma, it has to be equal to z over the resultant A, meaning that gamma is going to be equal to cos inverse of Z, it has to be -5. Just use the same -5. For cos and sine, you can use the same thing and you are going to get the exact angle. So here I'll say root of 30, like this. Okay, so if we try to punch this, gamma is going to be equal to, so say cos inverse of -5, you divide this by square root of 30, I close, we are getting 155.905. If we round off this answer, we are going to get 105.9, which is going to be equivalent to 156 degrees. That's how we find the angles for three-dimensional vectors. That's how we find the angles for three-dimensional vectors. Now, three-dimensional vectors, we have certain notations that we need to know under three-dimensional vectors. These notations, they move hand in hand with the axes that we know to say these are the axes that makes a three-dimensional vector. So here I'll say notations that are given to every axis. Notations. Now, what are those notations? So we have three notations with reference to the axes. X-axis has got its own notation. Z-axis has got its own notation. Y-axis has got its own notation. So X-axis, Y-axis, Z-axis. In other words, a vector can't even have these letters X, Y, Z, like the way I've, like what I'm doing here. We said A has to be equal to 2x plus y minus 5z. There are cases whereby they can't give you x, y, z in the vector. They are going to give you the same notations, of which if you have the same notations, they just mean the same things. So x is given with this notation, y is also going to have its own notation, and finally z. So x has got an I notation, I. Y has got the J notation. Z has got what we call a K notation. So in this case, this question was brought like this. It said A was supposed to be equal to 2x plus y minus 5z, right? In other ways, they can't give you my x, y, or z. They're going to write it like this. Then they'll write I, J. They mean the same thing. Don't even worry if a question has come like this and like that. They all mean the same thing. Meaning that where there is this, when you ever want to find the angle, where there is this, you are going to put this as what? Your x. Where there is this, you are going to write this one where there is part of y. And where there is this, you are going to use it on the part of z. Same applies when it comes to the issue of magnitude of the resultant, which is A. To find the same magnitude, you are going to use x, y, z by just writing it like this. Here I'll say A has to be equal to root of x square, y square, z square. Where there is this, you put the one which is found there. Where there is that, you put this one, and where there is this, you are going to put -5. Okay. Alright, now our main area here is to focus on what we call dot product and cross product. Our main aim here is to focus on what we call dot product and and cross product. What are these guys trying to explain to us if we say dot product and and cross product? So we are going to find that dot product and cross product, they all apply to both three-dimensional vectors and two-dimensional vector. they both apply to three-dimensional vectors and two-dimensional vector. So if we say dot product, the other word for dot product, they mean scalar. I'll say product. Okay? The other thing is, if they say cross product, they simply mean vector product. So don't get confused whenever they use words like scalar, they use a word vector, they simply mean cross product. Vector product is just one and the same like cross product. Dot product, it just means the same thing. Now, what are the symbols that we are supposed to be using whenever they give us something like this, and also they have given us something like that? What are the things that we should always be using for us to understand the concept? For dot product, we are going to be using the same word which sounds like the word, this one, dot. For cross product, we have to be using the same symbol for cross. Okay, so these two symbols, they all mean you have to multiply the vectors. But how do we multiply? We multiply vectors if we are using cross, if we are using dot and cross in different ways. We do multiply these things in different ways. How do we multiply? This is what I want to show you today. And what are we supposed to do if a question has come like this, they want us to find the angle? What are we supposed to do in that case? It becomes very simple for you to easily understand the concept here on how to use the cross product and also on how to use the dot product. We have two different formulas. That we can be using. The definitions for these two, I'll write them at the back. I'll just try by all means to write them at the back so that we understand and when to use the cross product and the so-called dot product. Okay. So if I start with dot product, so here I'll just define it like this. I'll say this is a product. This is the product of the magnitude of two given vectors cosine the angle between them. Okay, cosine the angle between them. Now, what does it mean if they say a dot product, a cross product? So I've defined it like this. A dot product simply means the product of two, or the product of the magnitude of two given vectors cosine the angle between them. What does it mean? If we have two different vectors, we have vector A and vector B. The formula that we can get based on the definition from this one is going to be like this. We are going to have A dot B has to be equal to the magnitude of A multiplied by the magnitude of B cos theta. That's what the definition is trying to tell us. And you'll find that mostly we normally use this formula if they say find the angle between the two vectors, you can use this formula. If they say find the angle between the two three-dimensional vectors, you can use this one. Okay,